Hello, in this video we want to look at seasons, keeping time, and calendars. So if we start with the seasons, we're all very familiar with those: spring, summer, fall, and winter, and what months they occur in. But the question comes up kind of why do those seasons even happen to begin with? And why do they get more pronounced the farther you are from the equator? Okay, so at the equator you kind of get the seasons are all very similar as far as the weather goes. And as you go farther north, the difference between, say, summer and winter is much more pronounced. Originally, it was thought that maybe that was because the Earth traveled in a elliptical path around the sun, and so when the Earth was closer to the sun, it was warmer. When it was farther away, it was cooler. But knowing that we get kind of opposite seasons and opposite hemispheres, that kind of debunks that. And also, the time when the Earth is closest to the sun, it is January, and so that's winter for us here in the northern hemisphere, so obviously not the warmest time of year for us. The reason that it does happen is because as the Earth rotates throughout the day, it is rotating on an axis that is not perpendicular to the orbit around the sun. It's slanted just a little bit, and so depending on our location in that orbit, we're presenting kind of a different angle to the sun. Okay, so as the Earth goes around the sun throughout the year, that angle stays the same. That axis is always pointing in the same direction here. I think the next graphic will show it a little bit better. Okay, so everything's flipped, but we still got the axis pointing off in the same direction, no matter where we are in the year, where we are in the orbit around the sun. And so if we start here at the summer solstice, the longest day of the year, we can see us here in the northern hemisphere, we are tilted towards the sun, and so we're getting the most hours of sunlight and the most direct sunlight during that time. As we move around, we get to the fall equinox, okay, the time when we've got equal daylight and nighttime hours. And so there, we're just kind of we're not getting a lot of sun, and we're not getting the least amount of sun. As we move down into the winter solstice, the shortest day of the year, we're in the dead of winter, and we can see that the northern hemisphere is tilted away from the sun. We're not getting as much sunlight as we were over here. And what we are getting is at a shallower angle, so a lot more of it reflects, and we're not getting the full heat benefit. And then we get back into spring equinox and back into summer. One other thing to note, we can see here, when we're having summer in the northern hemisphere, the North Pole is getting constant sunlight. Okay, so all day long there is sun there, and at the South Pole it's not getting any sun at all. And if we go all the way around to the winter solstice, it's exactly the opposite. The North Pole is not getting any sun, and the South Pole has 24-hour sun. Okay, I've got a quick animation to hopefully kind of show how that's working. So we're in the northern hemisphere right now, and you can kind of see the path of the sun as it goes around, and the tilt of the Earth, the axis there. So we're in April right now. So we kind of start the animation. We can see, right now we're getting a fair amount of sun. It's not the shortest time of year, and it's not the longest day of the year. Okay, so if I go forward into, say, June, now the sun is more directly overhead. We're getting more hours of sunlight. Whereas if I advance ahead, say, into December, it's now shifted all the way down, and we're tilted away from the sun. We're not getting as much sun. It's not overhead for nearly as long. Okay, so hopefully that kind of shows a little bit better what's going on. As I advance forward, we start getting more and more sun, and it'll come up, and we'll get more and more, and then it'll go back down, and we'll get less and less again. Okay. So that's why we get the seasons that we do. Okay, it's all about that tilt of the axis as compared to the orbit. If that axis was perpendicular to the orbit, then we would actually end up with, if this axis was perpendicular to the orbit instead of tilted, then we would kind of have those seasons being very similar, whether northern hemisphere at the equator or at the southern hemisphere. There would be some temperature changes based on the angle of the sunlight coming in, but the seasons would not be very different as compared to one another. So, moving on from seasons, we can kind of talk about how long a day is. Now, obviously, we, we've always measured days by the sun coming up and the sun going down, and midday being when the sun is kind of straight overhead or at its highest point. This is just the solar day, okay? And it's the time that it takes for the Earth to make one rotation with respect to the sun. Okay, so that is measured by sundials, and then you can look up water clocks sometime. They're kind of neat. They were a way to measure time accurately at night when the sun wasn't out. But that's the solar day, just measured strictly off of how long the sun takes to make one full cycle. Sidereal day is a little bit different. It's used more by astronomers because if we kind of picture looking at the sun, and obviously we're orbiting the sun in the time that it takes for the Earth to make one rotation. So if we just make one full 360-degree rotation, we would actually be not straight back to the sun again. Okay, we actually have to rotate a little bit farther to point back at the sun. So what a sidereal day is, it kind of takes that into account. It is based off of the stars, so an object clear outside of here, and it's actually a little bit shorter than a solar day would be. Okay, and it doesn't vary as much. It's much more accurate because we're basing it off of objects farther away, the stars. And one kind of side effect of that is that the stars rise 4 minutes earlier each day. Okay, so over time, we can see a different set of stars at a different time than we would have been able to. So, for example, if there was one constellation visible at 10 o'clock one night, since they rise 4 minutes earlier every day, after a few months, it might not be 10 o'clock, it'd be a totally different time. So, for example, if we're looking at, like I said, 3 months go by and it's 4 minutes a day, then 90 days times 4 minutes a day, that's now a difference of 360 minutes or 6 hours. Okay, so we're kind of on this cycle for the constellations and looking at different stars. They show up at different times of day or night. And sometimes, obviously, they're overhead during the day and we can't see them, so we have to wait for that cycle to come back around and be able to see them when at night. So that's what a sidereal day is. It's the rotation of the Earth as with respect to stars, so a lot farther away, and it doesn't kind of get messed up by being close to the sun. Okay. Apparent solar time is the time of the day just observed by looking at the sun. Okay, so it's all kind of based off of sunrise, midday, and sunset. So, of course, midday is when the sun is at its highest point overhead. The meridian is that path that the sun takes through the sky. So the highest point is the zenith, and that's what we would consider midday. And that's where AM and PM come from. AM just meaning anti-meridian before midday, PM meaning post-meridian after midday. Now, that was fine for all the times when we didn't have to communicate with other places. Okay, it didn't matter if midday for us was not midday somewhere else. Okay, it didn't really matter. But as things became more and more connected, and we could communicate long distances, midday did kind of matter. Okay, so if it was noon in one place, you didn't want to have to worry about it not being noon, 20 miles down the road, because it would be slightly different depending on your location when midday was. Okay, so a mean solar day is just the average of all of those apparent solar days. Okay, and it's defined as being 24 hours. So 24 hours is just what we've defined it to take for one rotation of the Earth. Now, like I said, if it was strictly observed, then time would be different on, say, one end of Nebraska than it is on the other end. The time at midday would be different by a few minutes. Okay, this is kind of why we need time zones so that we can agree between this line of longitude and this line of longitude were in the same time, and then change when we go over. Okay. And by the 1900s, most of the world had adopted the kind of standard 24 time zones. Um, and again, that coincides with technology mostly being able to travel quickly and communicate instantly long distances apart. It mattered a lot more what time we were all on. Before that, we could all just kind of synchronize to the sun wherever we were at, and that would be noon, and that was good enough for this town. Okay. Now, with the time zones, that meant that it was possible to, if you traveled, say, all the way around the world, you'd be gaining an hour, and then eventually you'd get back to where you started, and you would have gained a whole day. And that's where the date line comes from. Probably heard of the international date line. It was just the location was chosen to kind of affect the fewest people. Okay, it's almost all water, and these little jogs and diversions just make it skip over. So here it skips over Alaska, and here it skips over an island chain, and so that's just so that there's no real population being immediately split by the date line. But all that means is that if you pass over the date line, you have to correct either one day forward or one day back, depending on which way you're going. Okay. So if we kind of move into calendars, calendars have been around since ancient times. Back then, they were always based off of just the seasons or the lunar cycle, or looking at the stars, and so there was a lot of variance there. Um, there wasn't a lot of standardization. Obviously, every civilization kind of had its own way of measuring the seasons, usually based off the length of the day. Okay. So talk about calendars. We want to kind of define some of these. One day is, like I said, just the time that it takes for the Earth to rotate once, so 24 hours. 1 month starts to get a little bit more complicated because that's defined as the time required for one full moon cycle. You can look for moon cycles in another video, but one full moon cycle takes about 29 and a half days. Okay, so it doesn't divide out nicely. That is why our current calendars have roughly 30 days per month, just based off of those old lunar calendars. And then one tropical year, so the time required for one full orbit of the Earth around the sun, is 365.24 days. Okay, so even once we adopted a early calendars were 365 days, it was off because it didn't account for that 0.24 days that it actually took for the Earth to orbit the sun. Um, Now, different civilizations and governments would kind of combat that by adding a day here or there, adding a like a feast day or a holiday, and then that would kind of bring everything back into line. But it wasn't standardized at all. Okay. Before I go on to talk about the Julian calendar, it's widely believed that Stonehenge was a way to kind of set the time. A lot of the stones were oriented for being able to tell when the equinoxes were and when the solstices were, and then the ancient Chinese calendar that we've all heard about is based off of observations of stars. So they're both kind of examples of very old calendars. Kind of the first standardized calendar was the Julian calendar, introduced by Julius Caesar to kind of standardize the calendar across the whole empire, because dates could be very different from one end of the empire to the other. Like I said, they would just kind of throw in a feast day or a holiday here or there, and it was up to the regional governor, and so it wasn't standard at all. And so the Julian calendar was in use throughout the whole empire pretty much by about 3 AD, and every year had 365 and a quarter days. Okay, so that's pretty close to that 365.24 we saw a minute ago. And this was done just by adding a leap year every 4 years, or I should say, adding a leap day every 4 years. Now it was close, but it wasn't perfect because again, it's that 365.25 rather than 0.24, and so he actually lost a day every 128 years. The calendar would get one day off. Okay, so say for example, Easter would be celebrated one day earlier, one day closer to winter every 128 years, which doesn't sound like much, but over time, again, this was introduced in 3 AD, so by the 16th century, the calendar had lost 10 days. Okay, and they just wanted to do something about that so that eventually you didn't want to be celebrating Easter when in wintertime and then Christmas in the fall. So that leads us to the Gregorian calendar. Pope Gregory the 13th kind of introduced this as a way to bring things back into line, make up for those lost 10 days and um, not let it happen again. Okay, so it was widely in use by 1582. Of course, it was only initially adopted by countries that were under the influence of the Pope. Okay, so England and the colonies didn't end up adopting it until the 1750s, and that meant that for that intervening couple hundred years, the calendars were off between England and the continent. The way that they made sure that it wouldn't happen again, they kept the leap year every 4 years and did not have a leap year on century years that weren't a multiple of 4. Okay, so like 1800, there was no leap year, even though it was a multiple of 4 and should have been a leap year. There wasn't one, and then 1900 there wasn't one, and 2000 we did have one because it was the 4th century. It was a multiple of 400, so in 2000 we did have a leap year. Okay. And this calendar, the other one, lost one day every 128 years. This one only lost one or only will lose one. It hasn't lost one yet. It will only lose one every 3,216 years. Okay, so it's not something that we're going to have to worry about anytime soon. When it does happen, we can just adjust by one day. Okay, so that's kind of a. Oh, and they did have to, when they implemented this calendar, they had to jump 10 days. So I think they went from like the 4th of whatever month they were on, and then they just all the way anywhere that adopted this calendar, they just jumped from the 4th to the 15th in one day. And you can kind of read online that didn't go over well with a lot of people. They felt that they were being cheated by the government, losing those 10 days. It's kind of worth reading up on. But that's kind of an overview of the seasons and why we have them, keeping time, and calendars. Thanks.